Okay, I understand what's happening.
Elizabeth's out. So if you just try. Yeah, go ahead. All right, so all right. So, exponent rules. Again, a lot of this is review. You did learn these back in Math 1. You also may have already learned them in 8th grade, but there are going to be some new ones. So, in other words, we're going to go through these fairly quick. So, first things first, just some basic stuff with exponents. The basics that you need to know about exponents are the bases, the exponent, and the coefficient. So, of 2x to the 5th, which value is considered the base? X. So x is considered the base. So the base is the value raised to a power. What value is the exponent? Right, 5 is the exponent. So the exponent is the value of the power. Coefficient? Right. Now, coefficient in this case that definition has not changed. It's just the number in front of the variable. So the coefficient is the number in front of the variable. But another thing to note is that technically this 2 can also be considered a base. It's just raised to what power? 1. Now, that'll come more in handy when we do things like the power rule and some of the other rules. Now, you guys should definitely know this. What's the difference between x squared and 2x? X squared is equal to x times x. In other words, it's multiplying by itself. 2x, it's just twice 2. So, for example, let's just say the difference between 3 squared and 2 times 3. So, 3 squared, we know that's what? 9. Whereas 2 times 3 is 6. Now, what is the only number that if we plug it in for 2 and 0? So, if you do 0 squared, 0 times 0 is 0. 2 times 0 is 0. 2 squared is 4. 2 times 2 is 4. So those are the only two numbers where they're actually the same. Every other number, not so much. So exponents happen as a result of a value being multiplied to itself. So again, all of this stuff you should already know. This is just flat out review. So just to make sure you guys know, 5 cubed. If I wanted to write that out in expanded form, 5 times itself 3 times. So be 125. All right. So x cubed times x to the 5th. So expanded, how many x's is that? So we have 3 x's for x cubed, and how many for x to the 5th? 5. So how many x's total is that? 8. So I have the simplified version would be x raised to what power? X to the 8th. So essentially, what did we do with the exponents? We added them. So that comes to our first rule. If two expressions have the same base, meaning it's either the same number or the same variable, all right, what happens to the exponents when the expressions are multiplied? You add the exponents. So that means x to the m times x to the n is the same thing as x to the m plus n. You just add the exponents and keep the base the same. Never change the base. Now, something to note, because surprisingly, this does happen more than I care to admit. All right. Make sure you multiply coefficients so those numbers like normal. So for whatever reason, I found this happening in the past a lot. So for whatever reason, like if you look at letter C, for example, 7 and 2, for whatever reason, whenever they get into, the whole adding exponent thing, they also add the big numbers. You don't. What are we technically doing with those big numbers? Multiplying them. So these coefficients, 7 and 2, you still multiply them like normal. So if it helps, rewrite them with coefficients together and the like bases together. Why can I do that? Multiplication's commutative. I can move it around at my leisure. Just so it reminds you, okay, I got to do normal multiplication here and then add the exponents here. So 7 times 2 is 14. Now, same basis, but they're multiplying together, so I just have to add these x of it. So that's what that would be simplified. Now, 10 cubed. Shh. Come on, guys. Now, 10 cubed. How many 10s is that being multiplied to itself? 3. So if I didn't know what 10 cubed is, like let's pretend that you don't. Some of you may not, and that's okay. How can I kind of figure it out? 10 times 10, which is 100, and then times that by 10, which is... And that's how you can figure out without a calculator. 10 raised to any power is usually pretty easy to find. Every time you just keep adding a 0 to it. So 10 to the 4th is 10,000, 10 to the 5th is 100,000, 10 to the 6th, 1,000,000, so on and so forth. You just keep adding a 0 at the end. Now, this last one. So, x to the 5th, so let's say I expanded that. All right, so that's 5 x's times x to the 4th. So that's 4 x's. So how many x's is that total? 9. So it'd be x to the what? 9th. So if I actually did the... Guys, please stop talking. Shh. So if I actually did the rule and added the 5 and the 4, is 5 plus 4, 9? Yeah. So this would be x to the 9th. So guys, shh. If you need to expand sometimes to do it, like if the numbers are small enough, that's fine. All right? But you got to know these rules. All right, so let's just do a couple of examples. So let's do some difficult ones. Let's start with 8. So with 8, first off, right here, this is technically what? Negative 1. So if it helps, put the negative 1 there so you don't forget it's there. So I'm going to rearrange these so that all the like bases are together and all the coefficients are together. So what would my two coefficients being multiplied be? 5 and negative 1. What's my x? What's another set of like bases? The p's. So I'll do p cubed times p squared. And then the n to the 8th, it's just kind of on its lonesome, but we can't forget it. So all I did, guys, is just rearrange. It's the same problem. I just rearranged it so it's a little bit easier to see how to do it. All right. So all I did is put the coefficients together, so the numbers in front of all the variables. Multiply them together, because they have to be. Then I found the like bases, which in this case are the p's. Multiplying those two together. And I brought the m to the 8th down. Does everyone follow?
Yes.
And now I can kind of do each group individually to get my answer. Uh-huh. What do I do with these exponents? Add them, so it'd be p to the what? 5th, and then I bring down m to the 8th. And that's it. Now, if you put the m to the 8th first, it's whatever, because again, multiplication is commutative. Not really. The biggest rule of thumb is just make sure the big numbers are put in the front. That's really the only rule of thumb. All right. Try number 9 on your own. So try number 9 on your own. So I'll leave this one up as an example. So if it helps, rewrite it so you got all the like bases together. Because again, multiplication is commutative. Only more than welcome to do that.
Because it's in Oh, she almost laughed. That's fast. Right along. She saved this. He is. Yeah, no fish. You can't pass. You can't get above. I can solve big 20 is 10. And that big what do you think?
All right, thumbs up if you're ready.
I'm ready. I got
All right, so So what is my first move? Let's go. Where's my here? Elizabeth. All right, so we can multiply the coefficients first. So the 10 and 11, which is what? Is y'all's name Elizabeth? I don't think so. But it is 110. What's my next step, Peyton? My next step.
so the next step would be to combine G and G.
All right, so G cubed and G, which is what?
G to the power of
Right, because remember, this G has an exponent of what?
1.
1. So if you add them together, G to the 4th. What's your next move? Allison. All right, so I have H to the 8th times H to the 8th, which is what? Good. And then what's my last step? Graceland. Right, bring down that V to the 6, because it doesn't have anything to go with it. So this will be my final answer. Any questions on how the multiplication rule works? That one's probably the easiest of all the rules. Now, just for funsies, let's try 12. So, let's just talk our way through this. So if I reorganize this, starting with my coefficients, this will be 3 times negative 1. The x's, so x to the a It has nothing to multiply to itself. Y to the B times Y to the F. And then Z to the C times Z to the G. Now, these are exponents that are not powers, they're letters. So just think about the rules, yes?
Would you add the two letters?
Pretty much.
Combine them, so like Y.
But it would be 2y, or would it just be 1y?
It'll just still be 1y. So this would be -3. X to the A comes down. What will the Y be raised to? B plus F. Good. Because that's just the power rule. Not power rule, product rule. All right. What about Z? C plus G. Good. If you put G plus C, it's the same thing. So even though, there's no numbers there, you can still write out a expression. All right. Now, here's the one that most people hate, the quotient rule. So the easiest way to explain quotient rule is to just do expanded form first and then simplify. So x to the 9th, how many x's is that? 9. So I'm going to do 9 x's. All right, so that's 9 x's. Yeah, that's 9. All right, all over. X to the 7th, how many x's? 7. Now, here's my question. What can I do to simplify this? Right, just start crossing out because x over x is equal to what? 1. Anything divided by itself is 1. So you can cross out pairs. 1 for 1. 1 in the numerator, 1 in the denominator, you can cross out. So your answer is whatever you're left with. How many x's do I have left over? 2. Are they in the numerator or denominator? The numerator, so they stay in the numerator. So this would be x squared. So essentially, what did we do with the exponents? You subtracted them. All right. Let's try B. So, how many 3's on top? Sorry, how many 2's? 3. How many 2's on the bottom? 8. How many can I cross out between the top and the bottom? 3. So, this is what I have left over. How many is that? So, 2 to the 5th. Now, since everything canceled out on the top, it doesn't mean I can just get rid of the denominator. I mean, not the denominator, the numerator. What do I have to put up there? A 1. Yes.
Can't you just do the 2 times 2 and then 2 to the 8th power or something, and then get the fraction for that?
I mean, you could do 2 cubed and then 2 to the 8th and then simplify that fraction too, but that's because they're numbers. But sometimes, they become too big to do that. So just at least know the rule so you can always fall back on that. Now, what is 2 to the 5th?
That's 32.
32. So this would be 1 over 32. And if you didn't know that, that's why I made you guys grab a calculator. Now, we're still subtracting the exponents, but what happens? Right, so they went to the bottom because the denominator is bigger. All right. Now, I'll explain what that means for the rule in a second. So try C on your own. So expand it, see if you can get an answer. So I'll give you at least the expansion. Guys, this does not require talking. So I just expanded for you. Do some crossing. Guys, you do have a new Delta math, so just make sure you get the notes. You guys got it? How many 2's can I cross out? One set. How many X's? One between the top and the bottom. How many Y's? 2. How many Z's? None. So it's whatever you're left with. So I have 2 2's in the numerator, 2 X's in the numerator, 2 Y's in the numerator, and a singular Z in the denominator. So my numerator will be what? Well, it'll be 2 squared, X squared, Y squared. We'll simplify that in a minute. All over Z. And again, you can simplify 2 squared to be 4x squared, y squared over z. So, shh. Guys, please stop talking. Any questions on like the expansion method? So what happens when they're divided? You subtract the exponents. Now, that means if you have x to the m over x to the n, it's x to the m minus n. Now, here's what I usually tell my students, because sometimes you'll run into negative exponents, which we're not quite there yet. But honestly, this method's a little bit easier when you're trying to figure out where to put it back. I always subtract big minus small. So the bigger exponent minus the smaller exponent for the like base. And then put answer back where the big was. So for example, if you look at letter A, if I did big minus small, it would have been 9 minus 7. So the x squared would go back into the numerator because that's where the 9 was. Or if you look at B, if I did big minus small, it'd be 8 minus 3, which is 5. All right, now, since the 8 is the bigger, the 2, the 5th power goes back in the denominator. And then the numerator just becomes a 1. So that's what I mean by big minus small, put back where the big is. All right, it just makes it easier so you're not dealing with negatives. All right. So let's do some. All right. Let's start off with a relatively easy 14. All right. So if I did big minus small, what's the big one? Minus what? 8. So what would it be? 6 cubed. And where would it go? Numerator, denominator? Numerator. So I can cross that out because it's gone. I'm going to replace the 611 with 6 cubed. It's 216, yeah. So either one of these. All right, let's try a slightly harder one. Look at 17. So the 12, just going to stay where it is because we're not dividing it by anything. All right, what about the G's? What's my big minus small with the G's? 8 minus 3, so I got G to the 5th. Where's that g to the fifth go? Numerator, denominator. Numerator, because that's where the 8 was. So I can cross out the g cubed on the bottom, and the g to the fifth is going to go back here. Now, the h is, what's big minus small? 5 minus 4. So that's equal to h to the first, or just h. Where's it going? Numerator, denominator? Denominator. So you can cross out the h to the fourth because it's not going there. And you're going to put it in the denominator. So I'm just going to put an h here. So these aren't necessarily hard. You just got to be really careful. It can be a little bit finicky. All right. Now, we're also only just doing one rule right now. When we start doing a bit multiple, that's where, for a lot of you, it gets dicey. They're not, again, it's not necessarily hard. It's just a lot of times it's a question of where to start, or how do I know when I'm done? Because sometimes you have to do multiple rules and the order doesn't necessarily matter. All right. Last one, 20. First off, these coefficients, what do I need to do with them? Simplify them. So it's a fraction. Negative 2 over 10 is a fraction. We can simplify it down to what? Negative 1 over 5. Then from there, it's business as usual. So x is first. So I have x to the what minus what? 2 minus 1. So if it helps, if it doesn't have an exponent, you can go ahead and throw the 1s on there just so you don't forget they exist. So that'll be x to the first. Where's it going to go? Numerator, denominator? Denominator. So I'm going to cross out the x on top just so I don't confuse myself. Put it on the bottom. Now the y, it's on its lonesome, so we keep it where it is. And then the z's. So I have z the what minus what? 5 minus 1. So it's z the what? Fourth. Where's it going? The denominator. Clean this up a little bit. This will be negative y cubed over 5x z to the fourth. Someone's out. Don't know. I think Carson just went.
No, Carson.
And who's got the pass? Okay. All right. So, any question on quotient rule? Not too bad, right? Yes, no, maybe. Speaking out for hold your peace. All right. Now, this chart right here is what I expect you to at least know without a calculator, power-wise anyway. So let's try doing some of these together. So your squares, you should absolutely know. What's 2 squared?
4,
3 squared?
9,
9. 4 squared?
16,
5 squared?
25,
6 squared?
36,
10 squared?
100.
Now, the cubes aren't too bad because you just take whatever the number is squared and multiply by another of that number. All right, so 2 squared would be what? 8. 3 squared? 27, because 9 times 3. 4 cubed? 64. 5 cubed? 6 cubed? 10 cubed. Now, the fourths, all right? You at least need to know 2, 3, and 4. And again, it's the same thing. You just take whatever the cube was, multiply it by another of that number. So 2 to the fourth is? 3 to the fourth is? 4 to the fourth is? Good. And 10 to the fourth is 10,000. Now, for the rest, 2 to any power, it's super easy. Because whatever the number was previous, you just double it. All right? It's always just going to double. So what do you think 2 to the fifth is? 32. 2 to the 6? Tens are also really easy. All you do is just add on another 0 to the end for every power you do. So if 10 to the 4th is 10,000, what do you think 10 to the 5th is? 100,000. You just add on another 0. So 10 to the 6th is what? A million. So guys, I at the very least expect you to know all your squares because we did that in the last one. All right. And then anything else that's on this chart, I expect you to at least know. All right. Because my recommendation, the more you know at least this chart, the easier the simplification would be. All right. Doesn't mean that you still can't put in your calculator if you forgot, but trust me, the more you do, these are probably the most common numbers that you'll see. All right. Now, boys, just make sure you get through the rest of the notes and then delta math. All right, now we're going to keep on trucking. So now we're going into the power rule. So think about this carefully. 2 cubed raised to the 4th power. All right. It's almost like it's x to the 4th, but instead of it being x, it's 2 cubes. So this is the same thing as what? 2 cubed times itself 4 times. Which if we use product rule, what's 3 plus 3 plus 3 plus 3? 12. So 2 to the 12th. Say it again. You can. You could also write it as 8 to the 4th. You can also write it as, I think it's 324. If your calculator allows it, put it. Unless it's like a really stupidly big number, they start giving you scientific notation, then just leave it as an exponent. All right, what about p squared to the 5th? How many p's is that? 5p squared. So if we add up all those 2's, p will be raised to what power? 10th. So what are you noticing? What's going on here? You're multiplying the exponents here. When we expand them, we just do product rule. All right, but in reality, all you're doing is multiplying those exponents. So x to the m squared, this will be x to the m plus x, not plus, times x to the m. Let's think about this carefully. What do you think it would be simplified? X to the m plus m, right? Well, what's m plus m if you combine like terms? 2m's. So x to the 2m. Typically, you put coefficients first. That's just kind of standard. And isn't it true that if you multiply 2 times m, you get 2m? Yeah. So the fastest way is to multiply the exponents. So x to the, yes. Because m squared is m times m. M plus m, that's combined like terms. So it's really just the operation that's being done to it. So this rule, if you have x to the m times x to the m to the nth power, you just distribute whatever the power is on the outside to all of the exponents. This would be x to the m times n. So remember, something to note with this, because this is something that people forget. Distribute the power to all bases, including numbers. Biggest mistake I see with this is people forget to multiply it to a number. Like if they had like 2m in there, they would do 2m squared. It's not. It's 2 squared m squared. Which you'll see in a minute. Now, do I really need to bother with the expanded form for these, or do you just want me to go straight into simplified? Okay. So, for these, I always recommend putting ones on the bases that don't have exponents so you don't forget to multiply to it. All right. So, we're raising everything to the 2 power, so I'm multiplying every exponent for every base by 2. So 2 cubed becomes what? 2 to the 6. X becomes what? So if I simplify that a little more, because we know what 2 to the 6 is, it's what? It's 64 squared. Now, the next one is a prime example of why putting those ones is important. 8 is technically a base. So remember what I said, coefficients can also be considered bases. This is the main reason why you also consider it a base. So on the test, this is the main mistake that I see people do. They forget to multiply it to that number. All right. So always put ones for all the bases, not just variables. All right. So I'm going to multiply this 3 to all those exponents. This would be 8 cubed into the 6 p cubed. What's 8 cubed? You can put that in your calculator. It's what? 512. So this would be 512 into the 6 p cubed. $512 is just the same thing as 8 cubed. You just put it in your calculator to get that one. All right. So same thing here. I'm putting ones for every base that doesn't have an exponent, so I don't forget to multiply that 2 to it. So I'm going to multiply 2 to everything across the numerator and the denominator. Now, could you go ahead and do the quotient rule first? Yes. But for this case, let's just do power rule right now. This is one of those examples of order does not really matter what you do first. So 3 to the first becomes what? 3 squared. X to the first becomes what? 4 to the first becomes what? X squared becomes what? Good. Simplify some stuff down. 3 squared is 9. So 9x squared over 16x to the fourth. No. Right. So this is an example of they threw in another rule, which in this case is quotient rule. So if I do big minus small, that's x to the fourth minus 2. So that'll be what? X squared. Where does it go? Numerator, denominator. Denominator. So I'm going to cross out the x squared on top so I know that it doesn't exist anymore. So 9 over 16x squared. So guys, when I say I want it simplified, I want it fully simplified. If they throw in another rule and you see that there's another rule that you can do it. All right. So basically you keep going until there's nothing else you can do. So power of a product, make sure you multiply it to both bases. So this would be a to the m, b to the m. Same thing with the quotient. Multiply it to both bases. So a to the m over b to the m. Now, power rule is one of those rules that my recommendation is if you're trying to decide what to do first, do power rule first. So if it's one of those where you have multiple rules going on, my recommendation, do power rule first. All right, if it makes sense to do power rule first. So let's look at some of these. So let's look at. I have full confidence. You guys, do I need to even do like 1 through 12? Y'all pretty solid. You can do that? Okay. Well, let's look at some where you may want to do power rule first. Let's do 14. So this is one where you can 100% you need to do power rule first. All right. Do not try to do quotient rule until you get rid of that power rule in the denominator. Now, let's say that I was doing 12. Well, I guess not 12 because there's nothing to do there. Let's say I was doing like 10. 10, you could do quotient rule first and then do the power rule. Or you could do the power rule first and the quotient rule, doesn't matter. All right. But since this, for 14, since that power rule is kind of on its lonesome only in the denominator, you need to do it first. So I'm going to multiply this 3 to all my exponents, including the base of 5. This would be 20x cubed, that's left alone, over what? 5 to the power 3, because you're multiplying. And x what? 6. So make sure you multiply. So that'll be 20x cubed over 5 cubed is 125, x is 6. Right, now we can do quotient rule. So first start by simplifying this fraction. 20 over 125. What can I divide both of them by? 5. So that'll be 5 over what? Or 4 over what? 25. Now, quotient rule, big minus small. That'll be 6 minus 3 or x cubed. Where's that x cubed going to go? Top or bottom? Bottom, because that's where the x to the 6 is. So that's my answer. How are you guys feeling on these rules? Not too bad? All right. Go to page, so that's 5.1. We're going to scooch on into 5.2. So, go to page 7. It's just more rules. Might as well knock them out now. All right, so let's start by filling in this table. So this next part is zero exponents, negative exponents, and rational exponents. What's another name for rational? Not necessarily. Fraction. So rational, the root of the word is ratio. Ratio is another name for fraction. All right. So rational is just another fancy name for fraction. So fractional exponents. So let's start by filling this chart. What's 3 to the 4th? 3 cubed. 3 squared. 3 to the 1st. Now, if you put 3 to the 0 in your calculator, what do you get? 1. Now, don't yell out yet. You may already know this, but I don't care. Put 3 to the negative 1 in your calculator and tell me what you get. So you get 1/3, or if you're using my calculators, you'll probably get 0.3 repeating, which is just 1/3. Shh. Now, how many of you know how to convert to a fraction in your calculator, given a decimal? Well, that's a good piece of good knowledge to know, so let's go over it really quick. All right, so how to convert. So I'm going to put 3 to the negative 1 in. All right. As it stands right now, it's a decimal. Now, I highly expect you guys to know what 0.33 repeating is as a fraction. Good Lord. But let's say for whatever reason you didn't. Okay. The way you check is you hit the math key, which is under that green alpha key. Do you guys see where it says fraction at the top, or frac? Hit enter, and then hit enter again. It'll convert to its simplest form. So let's do it. So 3 raised to the negative 2. All right, make sure you're hitting the negative sign and not the minus. So you should get 0.1 all repeating, or as a fraction, math, enter, 1/9. So I more care about the fractions. So what do you think? And this one repeats, so I'm just going to cross it out. What do you think 3 to the negative 3 is going to be? 1/27. This will be 1/81. Now, here's my question. Why did I make you fill that out? Specifically the fraction parts. What's the what's the connection between negative exponents and the positive exponent counterparts? They flip. All right. So think about it. This is 81/1, 27/1, 9/1, 3/1. All right. They're reciprocals of each other. +4, -4. They flipped. Same thing with the 3s. +3, -3. They flipped. 2s are the same as well. And the 1s. So now 77 power is too big for us to get a nice number. But if I just want to leave it with the exponents intact, what do you think 3 to the negative 77 is the same as?
3 times 3.
77. 3/77.
So if I follow this pattern, all right, this is essentially the same thing as 1/3 of the first, 1/3 squared, 1/3 cubed, 1/3 of the fourth. So what do you think 3 to the negative 77 is? 1/3 of the 77. So in other words, all you do is just put in the denominator, make it positive. That's how you handle negative exponents. Flip the side of the fraction bar that's on, make it positive. Now, the zero property. So we know that anything raised to the 0 power is always 1. But you gotta pay attention to what's being raised to the 0 power. So only one of these is going to be 1. Which one? The top or the bottom? The bottom. Why is it the bottom and not the top? Parentheses. So you know how I've been drilling this in you guys' head for a while about the importance of the parentheses around the negative? All right. Same thing applies here. So -3 raised to the 0 power is just 1. However, up here, -3, 0, this is read as 3 to the 0 power times -1, or -1 times 3 to the 0. So 3 to the 0 is 1 times -1 is -1. So again, lesson in calculator. All right. That's why I always tell you, if you know you're squaring a negative number, make sure you put it in parentheses, because otherwise what happens? It's negative instead of positive like it's supposed to be. So, negative exponents. All right. So if you have x to the negative m, you'll have 1/x to the m. If you have 1/x to the negative m, this will be x to the m over 1, or just x to the m. So what I usually tell students, take the base with a negative exponent, just that base that's connected to the negative exponent. move it to the other side of the fraction bar, and then make the exponent positive. That's all you got to do with negative exponents. So like here, it was originally the numerator, moved it to the denominator. Here was originally the denominator, move it to the numerator. So let's do some of these. So we'll start out relatively easy. Look at number 3. So negative exponent is right here. I don't want it to be negative anymore. We don't like negative exponents. I want to make it positive. So what do I need to do with it? Move it to the numerator. So this becomes 3 cubed over 1, which is just what? 27. Positive 27. Number 4, 13 to the 0 is what? Shh. It's 1. That's an easy one. Huh? That's just the rule. So wherever it is around the fraction bar, if it's negative, you take that entire base with the exponent, move it to the other side, make the exponent positive. That's just the rule. So like for 2, or actually not 2. So like, for example, for 1, since there's not a fraction bar, I'm going to make 1. Put it over 1. To get rid of that x to the 14th, I'm just going to move that to the denominator, make it positive. This would be 1 over x to the positive 14. It's just the rule. Wherever it is originally around the fraction bar, move it to the other side, make it positive. That's just how you take care of a negative exponent. So now, number 5. This is another one of those cases where it doesn't matter which rule you do first. So potentially, which rules could I do first? You could do the product rule, or we could do the what? The negative rule. All right. So I'm going to show you both ways, just so you can see that you still get the same answer regardless of which rule you do first. So let's say I did product rule first. So that means I added these exponents. So I have 6x to the negative 6. But then I run into a negative rule. Now, be careful. What am I dragging to the denominator? X to the negative 6. Do not take the 6 with it. The 6 is its own base. You only want the base connected to the negative exponent. So this would be 6 over x to the 6. Now, let's say on the flip side, I did the negative rule first. So in other words, I put this over 1 and I move that negative 10. This would be 6x to the 4th over x to the 10th. But then I run to what problem? You have to do a, what rule? Subtraction or quotient rule. All right. So if I do big minus small, that's x to the 10th minus 4, which is x to the 6th. Where's it going? On the bottom. Yep. It's basically like what's actually happening to them, guys. So product rules, they're multiplying together.
Like if we do the rules, but we don't know their name.
I mean, on your test, maybe ask what rule do you do?
Oh.
Like the name of the rule.
Well, those people take choice or like
Well, if one of them is just different.
It's literally like the same, guys. Shh. It's literally like the name of what's going on between them, like what operation's happening. Product rule, that's another name for multiplication. Quotient rule, that's another name for division. Power rule, it's being raised to a power. Yeah, but you're technically dividing those exponents. So you're technically dividing the bases, but you're actually subtracting the exponents. So it's based off of what you're actually doing to the bases. All right, now, let's look at a hard one. Now, well, not necessarily hard. Now, 10 and 11 are very, very, very similar. But what's going to be the difference?
11 is going to be negative.
What? No.
Nope.
11's 1. 10 is 5 times 1.
Right. So 11 is 1 because this 0 is applied to all of this. So if I distributed, it'd be 5 to the 0, x to the 0, both of which is 1. But for 10, that 0 power is only affected to what? The x. So it's only the x that's 1. So 5 times 1 or just 5. So that's something that I also drill you guys on. Make sure that you know where the exponent's connected to. If it means to be connected to more than one thing, they'll put parentheses around it. If they don't put parentheses around it, don't assume. All right. So we can't assume that x to that 0 power was connected to this 5 because there was no parentheses around it. Here, absolutely we can assume. If I said these two are together. Now, 13. Oh, that just looks terrible, except this is the easiest one you'll ever do. It's 1. You don't have to bother simplifying that because it's all raised to what power? That's a big, fat 1. Don't you just love ones that are like that? You don't have to bother.
Oh, yeah.
All right. Shh. Take a minute. Let's see how you guys do. Well, actually, not yet. All right, look at 17. So, this one is one where you can either do the power rule first or you can simplify the inside first. Doesn't really matter. All right, so what do you want to do? Do you want to do power rule first or simplify the inside? Okay, so we'll simplify the inside first. So, I can first simplify the what? 4 and the 8 to be what? 1 over 2.
And then the D is 1.
The D's 1, so it goes away.
And then the C is the bottom.
C, the 5th, goes in the bottom. So I have 1 over 2C, the 5th, all cubed. Now I can do the power rule. So remember, put the 1s for the bases that don't have anything. So this would be 1 cubed over 2 cubed C to the 15th. 3 times 5, guys. It's power rule. 15th.
1 over 8 C.
3 times 5. It's not adding, you multiply. It's power rule. So, what's 1 cubed?
1.
2 cubed?
8.
C the 15th. That's it. Try number 18 on your own. No, I lied. Not 18, 19. Try 19 on your own. Good for you, Riley. Good for you. Again, it's kind of your preference. You can either do a quotient rule first, you can move the negatives first, whatever you want to do. Okay? I mean, it really doesn't matter where you start with this. But try number 19. Guys, how many times do I have to tell you? Stop touching each other.
Yeah,
And then
Y'all are how old? I should not be saying this. This is the kindergarten concept.
Xavier doesn't understand a lot of kindergarten concepts.
I do.
So,
I do understand
Oh, good God.
you can't read a clock.
What?
That's
Shut up.
Brian.
Yeah, exactly.
You were in this house, that's the most disciplined clock of all time.
I
You
can't
asked
read a
me
clock.
What sign it was.
The sun was like glaring off of it like the light.
Yeah, sure, but
It was, I swear.
is the sun there?
Save a lot.
Too?
Save a
What's
lot.
that one say?
That one says two.
That's 213.
Close enough.
You should be able
Good first grade.
Shut up.
remember in fifth grade.
You'd be surprised how many people can't read a normal clock. Like-
Knocked it to my wrist. Like, it's also wrong.
All right, guys, you got it done?
No, because they're just trying to. They're removing my
You guys ready to go over it? All right, so let's start with. Too big of a number. Let's start with Roberto. Which rule do you want me to do first? There's really no right answer to this. All right, let's do the negative rules first. So I'm going to take all my negatives and move them around. So I have -2 w to the 5th over 6 w squared y squared times y cubed. So all I did was take my negatives, move them around. Again, you could have done a division rule first. All right, it doesn't matter. My first period, they start with division. It really doesn't matter. All right. So from here, what can I do next, Abby? Simplify what? The fraction. Okay. So -2 over 6 can simplify to what? -1/3. So I have -1 w to the 5, 3 w squared, y squared times y cubed. Oh, yeah. Oh, yeah. There's more simplifying. We ain't done. So, basically, guys, if you can tell that you can do another rule, you're not done. Basically, you're done when you cannot do any other rule. All right. So, what's another way I can simplify? Let's go Colvin. Combine the y's. So, what rule is that, Colvin? It's the product rule. So, we add them together. So, it's be -1 w to the 5th, 3 w squared, 2 plus 3 is 5, so y to the 5th. What's the last rule? Well, that's the last rule. We got to do this quotient rule. So if I do big minus small, that's 5 minus 2, so w cubed. Where's it going to go? On the top. So your final answer would be -w cubed over 3y to the 5th.
Does it matter where you have the negative?
Technically, no. But honestly, the negative, I wouldn't really dock you for the placement of the negative just because it literally doesn't matter.
What?
Yeah, you could put -1. It's the same thing. Okay. Shh. All right. Any questions on the negative power rules and the zero power rules? So in other words, if I threw any of these at you, you'd be able to do it. Okay. All right. Last thing we got to talk about. We're almost done. This one's quick. Fractional exponents. Shh, Come on, guys, hang in there. We're almost done. So, fractional exponents. Now, we discussed this, not the fractional exponent side, but we at least discussed multiplying radicals in the last unit. All right. So, they have here square root of 3 times the square root of 3, which is 3. Why is that true?
Like they can't
Square root of 9 plus square root of 9 is 3.
Not really. That's so I was more getting at the square root of 3. This is the same thing as the square root of 3 squared. Guys, please stop talking. And square root and a square cancel each other out, leaving us with the 3. Now, we want to get that exact same answer, but now we're going to use fractions. So think way back to kindergarten. Think about them fraction blocks. If you are adding two fractions together and they're the same fraction, what two fractions, and they're the same fraction, what fraction added to itself gives you 1? 1/2. So if we did product rule, 1/2 plus 1/2 is in fact 1. So square root of x times the square root of x is obviously x, because for the same reason, square root of x squared, that's what that is. These cancel out, you're left with x. So again, what two of the same fraction add together give you 1? 1/2. So any square roots can be written as an exponent of 1/2. That is, the square root of x is the same thing as x to the 1/2. Now you may be wondering, why the heck does this even matter? It really comes into play when you do a lot more advanced math. Because sometimes you're just like, oh, I do not want to even deal with this root right now. So you change it to fractions, and then it makes it easier to simplify stuff. All right, let's look at some. What type of roots are these for the next ones?
cube roots.
Those are cube roots. So we're multiplying the cube root of 5 to itself 3 times. So that's the same thing as what? The cube root of 5 what? Cubed. Well, just like how a square undoes a square root, what do you think happens with the cube and a cube root? They also undo each other, which is why we get 5. So think back to kindergarten with your little fraction bars. What fraction added to itself 3 times gives you 1? 1/3. All right. So same thing here. Cube root of x multiplied to itself 3 times. It's the same thing as the cube root of x cubed. That cancels. We get x. So again, we're doing x to the 1/3. If we want to use product rule, still adds to 1. So a cube root can be written as an exponent of 1/3, such that the cube root of x is equal to x to the 1/3. So any radical can be rewritten as a fractional exponent. Any radical, whether it's a 4th root, 5th root, 6th root, whatever. Any radical can be written as an exponent. And how it works is, if you have the square root, let's say of x to the nth root, not square root, the nth root of x, all right? That means that x can be a cube root, it can be a square root, it can be a 6th root, it can be a 100th root, whatever. As a fractional exponent, it's equal to x 1/n. So whatever type of root you have, that goes in the denominator. And then you just put a 1 over it.
What if you have a 1/2? Is that just square?
Technically, you wouldn't see. The indexes are usually not fractions. So, here are some examples that they gave us. All right. So 16 to the 1/2, that's the same thing as the square root of 16, which is 4. 27 to the 1/3, that's the same thing as cube root of 27, which is 3, so on and so forth. So now the placement of the root also dictates what's being raised. So how can I rewrite the square root of 6 as an exponent? 6 to the 1/2. Technically, the unspoken number outside this radical is a baby 2. No. Square root of 6 is not 3. 6 raised to the 1/2 power is no.
But like, how would that? Yeah, how would you solve for that?
You don't. It's simplified.
It's the same way you solve for a square root.
It's the same. If I ask you to simplify that square root, it's not 6 times 1/2. It's 6 raised to the 1/2. Just like how 6 squared So 6 squared is 36. But once you get into fractional exponents, that's where roots come into play. So 6 to the 1/2 is the same thing as the square root of 6. Now, you'll see it a little bit more when we get into the ones that don't have 1 as the numerator. But what about this one? So I got to put 11x in parentheses because it's all under the radical, and I'm raising it to the what power? 1/2.
That's I actually have that answer on my slide.
How would you write that expanded?
You wouldn't. So you just have to know this rule. So now this one, be careful. The 2 is on its lonesome, so we just got to put it over here. It's the y that's only being raised to what power? 1/3. It's a cube root. Now, you can always write it, if it confuses you, you can always write it as 2 parentheses y to the 1/3. Just so you know there's clear separation, but just know that these two are the exact same thing. Now, on the flip side, number 4, be careful. What's the only value that's going under that radical? The x only. And what type of root is it? It's a square root. And then the 3 goes on the outside. Yep, that's it. What about this one? 4y's underneath the radical, and it's a cube root. And the same thing with this one. 5mn is all under the radical. And what type of radical is it? Square root. Now, that's very simple fractional exponents, but that's not always the case. Sometimes we have some more busy ones. So, just some vocabulary when it comes to fractional exponents. So, when it comes to reading a fractional exponent, x is your base, just like normal. Your actual exponent, or the power that you're raising x to, is 1, or the numerator. The root, so in other words, the type of root that you're taking of x is your denominator. So a square root will be taken because it's a 2. On the flip side, just know that your radicand is the value that's under the radical, and your index is the little number that's outside of the root that dictates what type of root it is. So if you hear me say the word index, I just mean the little number that dictates what type of root it is. So if it was a 3, it'd be a cube root. That's a 6, it's a 6th root, etc., etc. Now, why this comes in handy. This helps when we simplify these, all right, without using your calculator. So just so you know, rational exponent rule is if you have the square roots of n x to the a power, it could also be the square root of n to the x all raised to the a. Those are the exact same things. All right. You just see them written two different ways. I'm just showing you that they can be written in both those ways. As a fractional exponent, be x raised to the a over n. So in other words, you take whatever it's raised to, which is your a, that's your exponent, and then put it over whatever your index is, or your n. So, if I go back to the rule, so x to the 1/2 we already know is going to be what? Square root of x. 2 will be here, little 1 will be here, still the square root of x. Now, guys, stop talking. X to the 3/4. First off, what type of root's going to be? The fourth root. And x is going to be raised to what power? 3. You could also write it as the fourth root of x all cubed. It's the same thing. Doesn't matter how you write it as long as it's in one of those two. I just show you both so that you're able to recognize that they're the same. Because sometimes they flip-flop what you see. What about this last one? What would it be? Cube root of x squared, or you could write it as the cube root of x all squared. Now again, why is this important? Well, this helps out a lot when you have to evaluate fractional exponents with numbers. So, I'm not going anywhere. Just know, denominator of an exponent is the root, numerator of the exponent is its power, so it's being raised to. So think root. So if you don't remember root, think root, square root. All right. When you think of root, think of square root, cube root. All right. It's the type of root it is. So that's what the denominator is. It's the type of root. The numerator, it's a power. All right. So that's what's being raised to. So where this comes into play. All right. Let's look at C. So be careful with C. What that 4/3 exponent is only affecting the what? The x. So 2 is going to be outside of your root. What is your root? What type? It's a cube root, so I put the little 3. X is raised to what power? Good. So again, you just got to be careful of where that exponent, what it's connecting to. Now, look at B. Be careful with this because technically this is negative, which means what rule applies?
Quotient.
No,
Oh, wait, what's the quotient?
the negative rule. So I got to move this y to the negative 9/8 to the bottom before I can convert it. So this is 1 over y to the 9/8. So whatever your rational is, you're putting in the denominator. Now, I know that we've talked about like not putting rationals in the denominator. Sorry, radicals in the denominator. In this case, it's fine. All right. Yes.
Why does the y go down if
Because this exponent's negative, so the negative rule applies. Yes, but remember, whenever we move a negative exponent, that exponent becomes positive. That's why. So what type of root is this? It's an eighth root. Basically, the only fancy names are on the square and the cube. Everything else is like fourth, fifth, sixth, hundredth, whatever. And then y raised to what power? 9. Shoot. Oh, we're almost done anyway. Okay, now this next one is a prime example of how converting can help you evaluate. All right. So take note. The negative is with the 27. All right. So that means it will go under the radical with the 27. What type of radical is it? It's a cube root. Now, in this case, I'm going to put the exponent on the outside of the root because it'll help. It will help. Just trust me, it'll help. Smaller numbers. Now, this is technically not an imaginary number. We actually do get a real number for this. Because the cube root is different than a square root. Because what's the cube root of negative 27? Negative 3. Because remember, negative 3 cubed, that's negative 3 times negative 3, so that's positive, times another negative 3, so it's back to negative. Yes?
So what if we went like, rather than negative 27, it's 2/3 and negative 27, wouldn't that be like negative 18?
No.
If you multiply it.
No, it doesn't work like that, no. No, just no. So the cube root of negative 3 is negative 27. So this will be negative 3 squared, which is what?